Good afternoon, everyone. Thank you so much for joining us here in person and for joining us online for our second research seminar for 2023, which is being presented by Beth Temple. Before we get underway, I'd just like to acknowledge the traditional owners of the country that we're meeting on today, the Larrakia people here in Darwin, and to pay my respects to their elders past, present and emerging. I'll hand over to Beth Temple now to do her presentation. There's some time for questions at the end. So we'll go to questions in the room first and then questions to anyone who's online. Thanks very much, Beth. Over to you.
Okay, thank you. Good morning, everybody, and thanks for the opportunity to speak today. I would also just like to acknowledge the traditional owners of the land on which we meet today. For me, that's the Juru people of the Birragubba Nation, and to pay my respects to elders past, present and emerging. This talk is based on my PhD thesis, which I recently submitted through the London School of Hygiene and Tropical Medicine, and it's on the choice of pneumococcal vaccine for low and middle income countries. The data contributing to this work come from the first of two pneumococcal vaccine trials that we conducted in Vietnam. So firstly, just a brief overview. Many of you know already, but Streptococcus pneumoniae, or the pneumococcus, is a bacterium. It causes a variety of diseases, including pneumonia, meningitis, bacteremia, sinusitis, and otitis media. And pneumococcal diseases disproportionately affect young children and the elderly. There are 100 different pneumococcal serotypes, and these vary in their invasiveness and their ability to cause disease. And much of the disease burden is caused by a relatively small number of serotypes. Immunity is mostly serotype specific, which means that infection with one serotype does not necessarily protect against infection from a different serotype. This is important when it comes to vaccine development. So pneumococcal vaccination has a pretty long and interesting history. In the late 19th century, there was a series of experiments conducted on rabbits that used killed pneumococci. And it was shown that rabbits repeatedly injected actually were immune to reinfection. And these experiments also led to the discovery of serum therapy, because the people doing the experiments actually transferred the serum from the inoculated rabbits to other rabbits and showed that that transferred the immunity as well. The early 20th century brought about the first human pneumococcal vaccine trials. Those used whole-cell heat-killed pneumococcal vaccines, and they were tested on South African gold miners, but they paid no attention to the strain or serotype of pneumococcus that was used in the vaccine. Work on pneumococcal vaccines continued till about the 1940s, and then interest waned with the discovery of penicillin. But it picked up again in the 1970s, and another series of trials on South African gold miners, along with trials elsewhere, including the United States and Papua New Guinea, actually led to the licensure of the first pneumococcal polysaccharide vaccine by Merck in 1977. That vaccine included 14 of the pneumococcal serotypes, and in 1983, that was taken over by the 23-valent PPV that's actually still in use today. So polysaccharide vaccines are effective in older children and in adults, but they're not immunogenic in children under 2. And because much of the disease occurs in this age group, a new sort of vaccine strategy was needed to protect the youngest people. So that led to the development of pneumococcal conjugate vaccines, which use protein carriers conjugated to the pneumococcal polysaccharides, and that actually changes the immune response and renders the vaccine immunogenic in infants as well. The first PCV was licensed by Wyeth Vaccines, which has now been taken over by Pfizer, in the year 2000. So just looking at an overview of the current situation of PCV introduction globally, initially, for about a decade, the high cost of these vaccines limited their introduction to high-income countries. It wasn't until 2009 when Rwanda became the first low-income country to introduce PCV with support from the Gavi Alliance. Now, as you can see from this map, things look pretty good. There's a lot of green showing countries where the vaccine has been introduced. It's actually 87% of the world's countries have now introduced PCV either nationally or subnationally. But Some of the world's most populous countries are yet to introduce or still have subnational introduction. And furthermore, only about 2/3 of children with theoretical access to the vaccine actually receive it. And current estimates are that there are still 81.4 million children worldwide unvaccinated against PCV. Two approaches are needed to improve the global access. The first is better access where PCV has already been introduced, and the second is introduction to the remaining countries. And for those remaining countries, the choice of vaccine remains a key question. So just a quick overview of the different types of PCV available. The first was a 7-valent PCV, and its introduction led to dramatic reductions in invasive pneumococcal disease, or IPD. However, this was coupled with an increase in non-vaccine type IPD, so disease caused by serotypes not included in the vaccine, which led to the development of the need for higher valency vaccines. So there were two second-generation PCVs, PCV10, which is Synflorix, manufactured by GSK. That received WHO pre-qualification in 2009. And as you can see here, it contains the 7 PCV7 serotypes with the addition of serotypes 1, 5, and 7F. And the second is PCV13, which actually replaced PCV7. It's also manufactured by Pfizer, Prevnar 13. That received WHO pre-qualification in 2010. And that includes all of the PCV10 serotypes with the addition of serotypes 3, 6A, and 19A. More recently, a second 10-valent PCV has received WHO pre-qualification, and that is Pneumococcal, or SIIPL PCV. That's manufactured by the Serum Institute of India. And as you can see here, the two 10-valent vaccines, so PCV10 and Pneumococcal, differ in their serotypes that they include. So serotype 4 and 18C are in PCV10, but not Pneumococcal, whereas serotype 6A and 19A are in Pneumococcal, but not PCV10. Pneumococcal is currently in use in India, and rollout has recently begun in Timor-Leste, but it's not, to my knowledge, used anywhere else, and it won't be discussed further in this talk. Just very briefly, I won't go through this slide in detail, but this is just to illustrate that there are several higher valency vaccines either recently approved or currently in development. So there's always this sort of push to try and increase the number of serotypes included in the vaccines. It's worth noting that these are mostly targeted towards high-income countries, both in terms of the serotypes that they've selected for inclusion and also in terms of the cost. So the choice for low and middle income countries will remain between the two 10-valent PCVs and PCV13 for some time. So now to look at the comparison between PCV10 and PCV13. In terms of the formulation, as I've already shown, they contain different serotypes. They also differ in the carrier proteins that they use. The main point here is that PCV10, 8 of the serotypes are conjugated to protein D, which is actually a cell surface protein from non-typable Haemophilus influenzae. And therefore that vaccine actually has the potential to protect against not only pneumococcal infections, but also NTHI infections. So what are the ways that we can assess the effects of PCVs? There are 3 main ways. We can assess their immunogenicity, we can assess their effect on carriage, and we can assess their impact on disease. So immunogenicity data, before either vaccine was licensed, they were shown to be non-inferior to PCV7, which was the then used vaccine, at the post-primary series time point. And those measures were based on the proportion with serotype-specific antibody above a level of 0.35, which is a level used as a threshold of protection. And it's the main measure used for the approval of new PCVs. Then we have carriage data. Pneumococcal carriage is actually a prerequisite for disease, so a reduction in carriage usually corresponds with a reduction in disease. A reduction in carriage also reduces transmission and therefore extends protection to the unvaccinated portions of the community. And there's lots of data to show that the introduction of either PCV10 or PCV13 leads to reduced carriage, and that's in both the vaccinated and unvaccinated parts of the community, providing evidence for substantial direct and indirect effects. Of course, the goal of PCV programs is to reduce pneumococcal disease, and the efficacy and effectiveness of both these vaccines has been extensively reviewed. And it's been shown that introducing either vaccine leads to a dramatic reduction in vaccine type invasive disease, ranging from 60 to 100% reductions. And also they lead to reductions in pneumonia and otitis media. So all in all, there's a lot of data supporting the use of either vaccine. There are actually very few data directly comparing the two. And the current WHO position paper on pneumococcal vaccines states that there's insufficient evidence to determine if these two vaccines differ in their overall impact on disease, although it does note that for certain serotypes, 19A and 6C, PCV13 may offer advantages. So moving on to our trial, the Vietnam pneumococcal trial, we designed a trial that included a head-to-head evaluation of PCV10 and PCV13 in a 2+1 schedule, which is 2 primary series doses followed by a booster dose. This is one of 2 schedules currently recommended by WHO, the other being a 3+0 schedule with 3 primary series doses and no booster. At the time we designed the trial, there were no head-to-head data on these 2 vaccines. And our trial also had a second objective to evaluate different schedules of PCV10, but both my PhD and this talk are restricted to the comparison of PCV10 and PCV13. The trial was conducted in 2 districts within Ho Chi Minh City and was actually the first clinical trial ever conducted within that city. And it was coordinated from the Pasteur Institute. I've just got a few slides of some of the stuff we did in Vietnam. So we established 2 study clinics, and they had separate areas within each clinic for conducting informed consent, for sample collection, vaccination, etc. And then at the Pasteur Institute, we established a study office, and we also were able to use the vaccine storage facilities at Pasteur. We also constructed immunology and microbiology laboratories from what used to be a motorcycle car park into PC2 laboratories. So that was a pretty impressive feat. So the trial design, there were 6 groups recruited in infancy at 2 months of age. Those children received one of 4 PCV10 schedules, that's groups A to D in the table, or a 2+1 PCV13 schedule, group E, and we had an unvaccinated control group, group F, that received their first dose of PCV at 18 months. Initially, 18 months was going to be the end of the study, but we later got additional funding to extend follow-up to 24 months of age. And that meant that we needed to recruit an additional control group to provide unvaccinated specimens between 18 and 24 months of age. So group G was actually recruited at 18 months of age. Most of the head-to-head comparisons involve the 2+1 groups, groups C and E. In terms of the samples we collected both blood samples for the immunogenicity outcomes and MP swabs for the carriage outcomes. We were permitted to collect a maximum of 4 blood samples per child. So we collected samples at different time points in different groups, and some samples were only collected in a subset of participants. For the MP swabs, the time frame was the same in all groups, and swabs were collected at 3 to 6 month intervals. And the control group data for the swabs come from either group F, groups F and G combined, or group G, depending on their vaccination status at the time of sample collection. A quick look at the timeline for the study. The first participant was enrolled in September 2013, and fieldwork ran through to the end of 2016. The top photo there shows the first child enrolled in District 4, and the bottom photo is us celebrating the recruitment of the first child into District 7. So some statistics from the study. We enrolled a total of 1,400 participants, 1,201 infants in groups A to F, and 199 18-month-olds, group G. The consent rates were similar for the infants and the 18-month-olds, and both were very good, 84% for infants and 86% for the 18-month-olds. In total, we administered over 3,200 doses of PCV and collected close to 12,000 specimens, if you take into account the blood samples and the MP swabs. So now to move on to the results, the key findings of the study. This graph shows the difference in the percentage of participants with that antibody level above 0.35 post-primary series. Each dot represents a different serotype, and the line shows the 95% confidence interval. The dashed vertical line is the line of no difference, with data points to the left favouring PCV13 and data points to the right favouring PCV10. We pre-specified a 10% difference as being considered significant, and those solid lines show the plus or minus 10%. And these data show that for all serotypes, there was no difference at the 10% level because those 95% confidence intervals overlap the minus 10 to 10% range. And it's also worth noting that for most serotypes, over 95% of participants reached that level of 0.35. This graph looks busy, but I'll walk you through it. It shows the immunogenicity over time. The bars show the percentage above 0.35, and the lines show the geometric mean concentration, or GMC, of antibody. Each plot represents a different serotype, and time is shown on the x-axis. The first two rows are the shared serotypes, so the 10 serotypes in PCV10, and the bottom row is the PCV13 only serotypes. I really just want to focus on the pattern of the GMC, so the pattern of those lines over time, because a similar pattern was actually seen across the majority of serotypes. What we generally found was after one dose, although this data is a little bit difficult to see on the graph, PCV10 tended to produce higher antibody levels than PCV13. And this actually represents the first comparison of a single dose of these two vaccines in infancy. After the second dose, so post-primary series, PCV13, antibody levels tend to be higher than with PCV10. But by 9 months of age, so pre-booster, there was no clear pattern of differences. So for some serotypes, it was higher with one vaccine, and for other serotypes, it was higher with the other. Post-booster, PCV13 tended to generate higher levels again, but by 18 months, there were very few differences between the two vaccines. Now, the carriage findings. This graph shows the carriage prevalence and the vaccine efficacy against carriage over time. The lines represent the carriage prevalence, and the shaded bands show the 95% confidence intervals. And the text there is the reduction in carriage prevalence compared with unvaccinated controls, or the vaccine efficacy against carriage. The left column with the blue lines shows PCV10 in blue, and the right is PCV13 in red, with the black lines showing the unvaccinated control group. The top row represents PCV10 type carriage, and the bottom row shows PCV13 type carriage. And here we see the maximum effect at 18 months of age. And at this time, carriage was at its peak in unvaccinated controls and was actually in its lowest in terms of the post-vaccination time points in the vaccinated groups. We also looked at the most commonly carried serotypes in unvaccinated children, and we found that 87% of all the pneumococci carried over all the time points belonged to only one of 8 serotypes. The most common of those were 6B and 6A, and surveillance data from Central and Southern Vietnam also find serogroup 6 is common in invasive disease among children under 5. So this could have relevance for vaccine choice, but for the invasive disease data, we don't know the relative contribution of serotypes 6A, 6B, and 6C. Across all time points, we can see that just over half and 3/4 of pneumococci were PCV10 and PCV13 serotypes, respectively. And this suggests that the introduction of either vaccine would substantially impact the circulating populations of pneumococci in this community. So in conclusion, the data from our trial show that both vaccines are highly immunogenic. Responses to the first dose tend to be better with PCV10, and responses to the second dose and booster dose tend to be better with PCV13. But it's not known if this would translate to clinically relevant differences in protection. Both vaccines reduce carriage, and our data, although you couldn't see it on the graph that I showed, but our data suggests that PCV10 may have a greater impact on the carriage of the shared serotypes, and PCV13 may have a greater impact on serotype 36A19A carriage. So overall, they end up having a similar effect on PCV13 type carriage. In the interest of time, I wasn't able to show the data, but we also looked at the effect of PCV10 on NTHI carriage, and we found no evidence that PCV10 reduces either the prevalence or the density of NTHI carriage. We found that serotype 6A and 19A are commonly carried, and it could be very important, as I mentioned, the relative contribution of those different group 6 serotypes to invasive disease could have important implications for product choice in this setting. Overall, though, we can conclude that the introduction of either vaccine would bring significant public health benefits. And just a small comment to finish off, that there are also more potentially cost-effective alternatives for PCV introduction into Vietnam and to other countries. And these include the use of Pneumococcal, which has a lower price than PCV10 or PCV13, and also has the advantage of including serotype 6A. And also looking at schedules with fewer doses. That was actually the subject of our second trial, and perhaps we might be able to present some of that data later this year. I'd just like to thank everybody who made this research possible. It was a big collaborative effort, and thanks for everyone supporting me throughout my thesis. Thank you.